Hey, you guys. All right, here is the last lesson for this series unit before we get into all the preparation, okay? This is called Error Bounds in Power Series. Okay, go ahead and write down the FLT and press play whenever you're ready. So, given a series, you're going to be able to know how and when to apply two types of error bounds, okay? So, the first one is the alternating series error bound, okay? The second one is the Lagrange error bound. Okay? It sounds very complex, but it's not that bad, you guys. I'm going to tell you guys now, most of the people that take the exam don't do well on this question because it's the first thing that gets cut out of their curriculum because they're running out of time. Now, thankfully and fortunately, you guys have all the time in your hands here, okay? So we're able to really look through series in a very detailed manner, and this is why you guys are going to score so much higher than everyone else globally, okay? So, you want to walk out with this. What is the alternating series error bound? What is the Lagrange error bound? And how do I know when to use it? Okay? So here we go. Here, you should have received a text from me by now to download this worksheet. I don't want you to write everything down, so please just print it out and then write over it, okay? Because there's a lot of verbiage here. So first, okay, we're going to review a little bit before we get to our airbound question, okay? So here, we're just going to take a look. We're going to ignore everything that's written up here. And we're just going to jump to this FRQ released question here from 1995. Although it's a long time ago, this question still applies, okay? So here we go. Part A, a little bit of a review for you guys. We want to write the first four non-zero terms and the general term for the Taylor series expansion of f of x centered at x equals 0. All right? So this is what you guys are used to. You take a look at f of x. F of x is something exponential. So you start off with what you know, and then you build off of it. So we know that e to the x can be expanded out to, and this is where you want to pause and see if you can recall the expansion for e to the x. Press play whenever you're ready. So remember, e to the x is everything, right? So it's going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, right? Notice how they said first four non-zero terms. I have 4 exactly right here. So I'm going to go ellipses. And then this is where I squeeze in my general term. My general term is going to be x to the n over n factorial plus dot 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 to make it go on forever and to make that equal, okay? All right, I have e to the x, but f of x is e to the negative 2x squared. So what I'm going to do is I'm going to replace x with negative 2x squared. So here we go. It's going to be 1 plus negative 2x squared plus negative 2x squared over 2 factorial plus negative 2x squared cubed over 3 factorial. Make sure that you guys have your quantities in place. Plus dot 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 negative 2x squared all to the n power over n factorial. Notice all I did was I replaced every x with a negative 2x squared. You do not have to simplify it because equal is equal. We have our first 4 non-zero terms, and we have the general term. That should give you about 3 points right there, okay? Okay, part B. Find the interval of convergence for the power series f of x. Okay, show the analysis that leads to your conclusion. Go ahead, press pause there, and play whenever you're ready. Find the interval of convergence. Okay, so by now you've had a chance to find the interval of convergence. You find out that the interval of convergence is from negative infinity to infinity. But look, if you use the ratio test, okay, you're not wrong, but you wasted your time. If you guys remember, back with the, where can I find it? Back with the Maclaurin series, I had you guys fill this out and take a look at that, the interval of convergence. So since we're dealing with e to the x, check that out. You could totally avoid the ratio test. Okay? So don't be too mad at yourself if you did it the long way. But that's what that's there for. Okay? So it can save you a little bit of time. So that was just from your chart. All right? Okay, and then usually the last question of your series FRQ is an error question. Okay? We'll talk more about the patterns later when we get to the packets, all right? But first, let me talk to you guys about what error bounds really is, okay? If you think about any type of production company, okay, when you're building something, okay, especially when you're manufacturing something at a large scale by volume, you want to know what your error is in terms of, let's say, we think about IKEA furniture, right? When you're constructing these, you know, when we take IKEA furniture home, there's still a large chance that we can mess up. Not because we failed to follow instructions, but by the way that we drill in our nails and our bolts, it could throw off where that nail and that bolt is going to end up. That error determines how well your furniture is going to come out. So this, in theory, what we're really figuring out here is how close are we in terms of the exact function, okay? And how far off is our error? So think about this here. We'll come back to this in a second. Now, suppose we're dealing with the cosine function, okay? Cosine function expands out to pretty much every even degree function, which I have over here. I just wrote the first three terms. It goes on forever. So this here is just an approximation. Okay? What if I wanted to figure out the cosine of 1.3? Okay? Go ahead and type that into your calculator right now. Make sure you're in radian mode. Okay? You should have an answer. All right? Now what I want you to do is, using our polynomial lookalike, okay, what would happen if I were to plug in 1.3 into our x here? Okay? I want you to go ahead and plug this into your calculator and then write your answer here. Okay. So if you don't have it yet, please press pause, okay? But if you do have it, go ahead and continue. So this is what you should have gotten. Okay? If you were to type in cosine of the 1.3, you would have gotten about 0.26749882886. I didn't round it, okay? Now, if you were to use our polynomial lookalike, you would have gotten 0.27400416667. Okay? Now, were we close? How close were we? And how far were we, right? Okay, so this is our actual, and this is our polynomial lookalike. How would you guys find the error? How far off were we? Okay, so if you want to find the error, you would have to subtract one from the other. Okay, it doesn't matter which way you subtract it. So what happens is you take your actual, which is your f of x, in most cases, okay? And you subtract it from your approximation or lookalike. Now, it doesn't matter which way you subtract it, so I'm going to put in absolute value bars here because you're really just finding the distance, okay? So remember when you guys had the sine graph and then you had the polynomial lookalike, right? What you're doing right here is you're trying to find out how far off was your approximation to your actual, okay? So we're finding the distance between the two, all right? So this alternating series error bound tells you that your error should not be anything more than the next term, okay? The next available term. Okay, so the next available term, so notice how we used the first three non-zero terms. So the fourth term is going to be your maximum error, okay? So the fourth term right here is negative x to the 6 over 6 factorial. So this is the n plus 1 term, and this is the n, the number of terms that we used. So in this case, what we're going to do here is we're going to have negative x to the 6 all over 6 factorial. Okay, and we're going to evaluate this at 1.3. All right. Now it's easy because we have the two values here highlighted already. If you were to subtract these two, oh gosh, let me do this here. 0.26749888286 minus 0.27400416667. Okay, you get something about negative 0.0065 and so on. Okay? So it's easy when we have the two actual values to compare it with. But oftentimes, you're only given one and not the other. So you need to rely on the next available term to determine how far off your error is going to be. This is going to make a lot more sense when we actually do a problem. So don't worry. Don't get too overwhelmed here. Just take a look. Here we go. Okay, so first the when, okay? Alternating series error bound. Okay, we'll call it ASEB for short. Alternating series error bound. When do we use it? Very simple. When you have an alternating series. Okay? When you have a series that alternates, you're going to be using the alternating series error bound. That's it. Okay? So here I'm going to read you a little bit. When a series is alternating, the error is maximized in the next unused term. What I want you guys to do is cross that out and just think of the next available term. And I'll tell you what I mean by that, okay? So here we go. Here's part C, the part that we didn't get to do yet. We first know that this is an error question because you see something like this. The absolute value of f minus g. You're finding the distance between the two functions, which is pretty much code for error. Okay? Other problems, they actually might literally use the word error so you know, but sometimes they don't, like this one. So here we go. Let g be the function given by the sum of the first 4 non-zero terms of the power series for f of x. Show that the error is less than 0.02. Here's what you guys do. Because we used 4 non-zero terms, okay, the error, or the absolute value of f of x minus g of x, has to be at most the next available term. So if we used 4 non-zero terms, we have to use the 5th term here. So if you take a look, this right here is f. Here are, I'll highlight it in yellow. Here are the first 4 terms. Okay, so if we're trying to calculate what that error is, we look at the next available term. Well, what's after negative 2x squared cubed over 3 factorial? That next available term is going to be negative 2x squared to the 4th over 4 factorial. This is what we're going to be using. And it's going to go right here. Negative 2x squared to the 4th over 4 factorial. Okay. Now, if f of x was the sum of the first 6 non-zero terms, then the error would be based on the 7th term. Okay. If you had f of x that represented the first 20 non-zero terms, then the error is going to be based on the 21st term. All right. So here we go. What you're going to do here is you're going to evaluate this at. Now, where they give you the value is different in each case. Here, they wrote it in an interval. You're actually going to use 0.6. All right. You can use negative 0.6, but then it's just easier to use the positive value. So if you were to plug and chug this, okay, I'm going to do this with you. So 0.6. 0.6 squared times the negative 2, okay, all to the 4th power. I'm doing it on my calculator, so it's taking forever. Divided by 4 factorial, or 4 factorial is really just 24. I end up getting 0.011 if you were to round that correctly, okay? Now, here's the thing. You guys could definitely cheat a little bit. So here's what we do. Now, here I know in 1995 it says calculator is allowed. You guys should know the series question is always going to be number 6 on your FRQ exam. So you know number 6 is non-calculator. Way back in the day, they allowed a calculator, but within the last 15, 20 years, they stopped allowing it. So what you guys can do is you can be an a-hole about it and do this. Well, I can just plug in negative 2 times 0.6 squared all to the 4th over 4 factorial. And then show that it's less than 0.02. Okay. Now, I actually calculated it on my calculator here. I want you to know that this does come out to 0.011, which is definitely less than this. But who cares, because equal is equal. Okay? But you have to have this part here. If they're asking you to show it, you have to physically write it. Okay? This is going to make a lot more sense when you do these problems more and more. So give yourself an opportunity for growth. Okay? All right, here we go. Here is example 2. Okay? Go ahead and do part A real quick and press play when you're ready. Okay, so if you forgot what the Maclaurin series is for the natural log of 1 plus x, you would have to reinvent the wheel. Okay? Or if you remember the common Maclaurin series, the common Maclaurin series over here for the natural log of 1 plus x is just x minus x squared over 2 and so on. So make sure you guys have these out in front of you here, okay? All right, so here I have x. Let me rewrite that. So the natural log of 1 plus x is equal to x minus x squared over 2 plus x cubed over 3. Now, they're asking for the first 4 terms, so I need to add one more. So minus x to the 4th over 4 plus dot 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 plus the general term here, negative 1 to the n, x to the n plus 1 over n plus 1 plus dot dot dot, which makes it equal, okay? All right, so we have that. And just from that, you would earn about 3 points, okay? Reinventing the wheel, you could do it, but you're wasting a lot of time. Time that you could definitely use elsewhere, okay? All right, for what values of x does the series in part A converge? AKA, what is the interval of convergence? Okay, now you could use the ratio test here, but we have it right over here, you guys, the interval of convergence. For the interval of convergence, for the natural log of 1 plus x, it's just from negative 1 to 1, including the 1. Boom. So easy. All right. By now, you probably already scored 4 out of the 9 points already, which is more than enough than what you need. But we're going to aim for 9 out of 9. Okay? Because that's how you guys are going to get your passing score, but also that's how you're going to save all those dollars in college. Okay? Here we go. Estimate the error in evaluating natural log of 3 over 2 by using on the first by using the first 5 non-zero terms. Okay, estimate the error. So what are we going to do here? So if you want to find out the natural log of 3 over 2, again, 3 over 2 is the same thing as 1.5, okay? That means x right here has to be 0.5 or 1/2 equivalently. All right? So the first 5 non-zero terms, here we go. If we want to estimate the error, right? What do we need to know? Think about that. Pause. Press play whenever you're ready. If we want to know the error, estimate the error, okay? How do we figure that out? Keep in mind that there is no calculator here. Okay. So what we do is we create an error bound. So my question to you guys is, can we use the alternating series error bound? Absolutely, because this series is alternating, all right? So what we do here is, if we want to estimate that, x is equal to 0.5. Just keep that in mind, all right? So what we want to do here is, we want to find the error, okay? The absolute value of f minus g, that's already understood to the AP readers that means error, okay? We know it's going to be at most what, right? So if we're estimating the first 5 non-zero terms, what's the maximum error, right? If we're using the first 5 non-zero terms, we're going to have to use the 6th term. The 6th term is going to be x to the 6th in this case over 6. And I believe, hang on, this is going to be plus x to the 5 over 5 minus x to the 6 over 6. So it's a negative. Okay? So our error is going to be negative x to the 6 over 6 evaluated at 0.5. So this is going to be negative 0.5 to the 6th power over 6, and whatever that comes out to. But we really don't care. We don't have to show that it's going to be less than something because of the phrasing of the question, so you're pretty much done. Okay? But just for the sake of understanding this, I'm actually going to crank out the numbers for you guys. Here we have 0.5 to the 6th power divided by the 6. I'm going to ignore the negative because it's the absolute value of. I end up getting 0.003 if you round it. So what that is saying is that if you were to approximate the natural log of 3 over 2 using the expansion, you would be really close to the point where the error is only 0.003. Okay? And that's it. Part D, we'll skip. We'll come back to that later. Let's try one more. Okay, here's 2010. Notice how it's number 6. Okay, I think it's been number 6 for the past 20 years, I think. Okay, but it goes pretty far back. All right, here we go. F of x is this piecewise function here. And then they tell you, let me get rid of that. They tell you that g of x is this. 1 plus the integral of f. Okay? Write the first 3 non-zero terms in the general term. For cosine. Okay, so let's just look at that. Okay, so cosine. Fill in the blank there. Press play when you're ready. Cosine, I remember, is all even degree functions. So it's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And there goes my 3 non-zero terms. Sometimes they ask for 3, sometimes they ask for 4, okay? Plus dot dot dot. The general term is going to be negative 1 to the n, x to the 2n over 2n quantity factorial plus dot dot dot, so that I could say that they're equal, okay? Okay, right there, you would have gotten, I believe, 2 or 3 points already. Now they ask you, use this series to write the first 3 non-zero terms and the general term for f, okay? About x equals 0. So centered at 0, so when we're really close to 0, we're looking at this function here. And this is where you guys build. It's not too transparent, but here we go. You have cosine x. So we could easily get cosine x minus 1. Because, take a look. If I want cosine x minus 1, I would have to just subtract 1 on the other side. I'll use this in different colors, okay? Let me let's see if I can copy paste that. Yeah, not bad. Okay. So let me get rid of the highlight. All right. If I wanted cosine x minus 1, I'm just going to put a minus 1 there. And what I do to one side, I do to the other. But notice how the red 1 at the beginning and the minus purple 1 at the end will cancel out. Boom and boom. So I'm actually going to erase those. Now that I have cosine x minus 1, what do you guys think we do if we want cosine x minus 1 all over x squared? Okay. All you would have to do is divide every term by x squared. Okay. Now, there is a little bit more to it. If you guys notice, it says the first 3 non-zero terms. Because I got rid of that 1 at the beginning, I actually only have 2 terms right here. So I'm going to go ahead and bump that over so that I have room. So that next term should be minus x to the 6 over 6 factorial. And I'm going to go ahead and divide that one by x squared as well. Okay. Again, I'm not going to simplify because I'm a jerk and I want the AP readers to do their work. Right? But also equal is equal, you guys. So take a look. We started with cosine. Then we built in the minus 1. Then we divided it by x squared. You guys will do this a lot where you start off with something that you know and then you build off of it. Okay? I believe in this question you would have earned at least 4 or 5 points already. Okay? But I'll double check. And that's it. Okay? Now part B is where we'll skip for now. Yeah, let's skip that one. but we will get to it, so don't worry about that, all right? Here's part C, okay? We want to write the fifth degree Taylor polynomial for G about x equals 0. So if you guys remember at the very beginning, G is this function right here, 1 plus the integral of f. I'm going to go ahead and write that. So I know that G of x is 1 plus the integral of f of t dt from, I think, 0 to x. Let me double check here. Okay. Cool. We also know that f of x, our expansion was hold on, you guys. F of x was cosine x minus 1 all over x squared. Yada, yada, yada. But we were able to expand that to... I'm going to copy paste this here. Just so that we have everything in front of us, okay? Okay. So, to make things a little bit easier, all right? This right here, now I'm going to clean it up just because it's going to make my life easier for this problem. So if you take a look at the first term, x squared divided by an x squared, that's going to reduce out to a 1. So that's 1 over 2 factorial. So that's negative 1 over 2 factorial. The next one is going to give me 2 x's left over, so that's x squared over 4 factorial. The next one is going to leave me with 4 x's at the top over 6 factorial, and so on, okay? Now, that's the expansion. It keeps going, okay? So that's the expansion for f. G is 1 plus the integral of f. So 1 plus the integral of all that. I'm going to group that so that it's proper. dt 0 to x. Okay? So here's where we are, okay? 1 I can just bring down, so that's going to be 1 plus. When you integrate, you guys should know how to integrate every term here. Negative 1 over 2 factorial. If you integrate a constant, it becomes negative x over 2 factorial. Okay? The next one is going to be x cubed over 3 times 4 factorial. The next one is going to be x to the 5th over 5 times 6 factorial. And so on. Okay? But notice how they only ask for the 5th degree. So there's our 5th degree right there, you guys. Okay? We don't have to keep going. And that's it. Now I'm rushing through this part because our main concern is with error bound, okay? So here's the last part. The Taylor series for G about x equals 0 evaluated at x equals 1 is an alternating series with individual terms that decrease in absolute value to 0. Nobody cares about that. Use the 3rd degree Taylor polynomial for G to estimate G of 1. Explain why this estimate differs from the actual value by less than 1 over 6 factorial. Okay, first off, how do we know that this is an error-bound question? Right here, I'll put it in pink. Explain why this estimate differs from the actual. Estimate differs from the actual. When you're subtracting the estimate from the actual, you guys are finding the error, okay? So they won't always use the word error, so watch out for that. So let's go in order. We want to use the third degree Taylor polynomial for g. Okay, so that's going to be 1 plus negative x over 2 factorial plus x cubed over 3 times 4 factorial. That is the third degree Taylor polynomial for g. Now what they want us to do here, so Taylor polynomial sub 3, that's how you guys would write it. Okay, so here we want to estimate g of 1. So g of 1 is going to be the third degree Taylor polynomial at 1. So we're just going to plug in 1. Okay. This is a non-calculator question, so I'm going to leave it as is. Equals equal. Okay. Explain why this estimate differs from the actual value by less than 1 over 6 factorial. That's code for error. So here we go. The absolute value of f of x minus g of x. Remember, this right here is error. Okay, will be maximized by what? Right? Remember, it's always going to be the n plus 1 term. So how many terms did we use for the approximation of g of 1? We used the first 3 terms. So the next available term is going to be x to the 4 over 4. Hold on. Just kidding. The next available term is right here. Okay, since we used the first 3, the error is going to be based off of the next available term. So that's negative x to the 5th over 5 times 6 factorial. Notice how I have absolute values there, okay? Make sure that you guys don't forget that. And I want to evaluate this. Well, where did I make my approximation, right? My approximation was at 1. So here's what we do. We plug in 1. So negative 1 to the 5th power over 5 times 6 factorial. Now, this is definitely less than 1 over 6 factorial. That's how you guys cheat. But really, just to show you guys, if you clean this up here, that comes out to 1 over 5 times 6 factorial. And by now, you guys should know that that's definitely less than 1 over 6 factorial because you're making your denominator larger, okay? But again, you don't have to evaluate it. You could just, if you know your steps, you know you're going to be right, you could just make the statement that it has to be less than. And there you have it. Okay? Here's the last part. So, alternating series error bound, you use it when there's an alternating series. We always use the next available term. Okay? Alternating series, next available term. Now, when your series is not alternating, you resort to this guy over here, the Lagrange error bound. So I'm going to tell you guys right now, the Lagrange error bound you use when your series is not alternating. Okay? There you go. Right there. Boom. Now, how you find the error bound is a little bit different from how you find the error from the alternating series, okay? There's a lot of verbiage here. You're going to use the n plus 1 derivative, okay, as the maximum value. That corresponds, which is pretty much the same thing. This right here is the next term, but what I want you guys to circle or highlight is this right here. You're not using the next available term, okay? You're using the next unused term. So the only way to make this a little bit more clear is the next term, whether visible or not. Okay? And I'll show you what I mean by that when we do a problem, okay? That's the only thing that makes it a little bit different. All right, here we go. I'm going to do part A for you guys to speed up the error question, okay? Here we want the third degree Taylor polynomial centered at x equals 2. So this is going to be f of 2 plus the first derivative with the first degree with the first factorial plus the second derivative, okay, the second derivative, second degree, second factorial, third derivative, third degree, third factorial. This is the long way. The reason why I have to do it the long way, you guys, is because they don't tell me what I can start with. In the last problem, we had e to the x, we had cosine x, so we had something that we could start with. There are some occasions where they don't give that to you, so we have to reinvent the wheel, okay? So here we go. F of 2 is given as -3 right there, plus 5x minus 2 to the first power over first factorial, but I won't write that, okay? Plus 3x minus 2 squared over 2 factorial minus 8x minus 2 to the third over 3 factorial. Okay, so I don't have room, so I'm going to bump this guy up. So there we go. Now what they want you to do is use it to approximate f of 1.5. What are you going to do? You're going to stick in the 1.5. And what do we do next? We do nothing because equal is equal. It's going to save you so much time. All right? Cool. Okay. Part B. The fourth derivative of f satisfies the inequality that the fourth derivative can be at most 3 for all x in the closed interval from 1.5 to 2. Use the Lagrange error bound to approximate f of 1.5 to explain why f of 1.5 cannot be -5. Okay, what the heck are they asking for, right? So they're saying if we can figure out the error, we could use the error to show that it's impossible for f of 1.5 to be -5. Okay? So here we go. Your error, you could even write absolute value of f of x minus g of x, doesn't matter, will be at most the next unused term or the next term, whether it's visible or not. Okay? That's not going to make any more sense until we actually get to a problem where it does fit perfectly, okay? So here, we're using f of 1.5. Remember how they asked us to find f of 1.5 at the beginning? So we used this here, and notice how we went all the way up to the third degree. But in this case, 1, 2, 3, 4 terms. So our error is going to be based on the next term, the fifth term, which should be the maximum of the fourth derivative of x minus 2 to the fourth over 4 factorial. Okay? So that next term that we did not use is going to be right here. It's going to be whatever that fourth derivative is, x minus 2 to the fourth over 4 factorial. That's going to be your error. it looks very similar to the alternating series error bound, okay? The only thing different is we need to know the maximum of our fourth derivative. They tell us right here that it has to be 3, but we want to evaluate this at 1.5. So here we go. This is going to come out to the absolute value of 3 because that's the maximum. That's the most that the fourth derivative could be. 1.5 minus 2 to the fourth power over 4 factorial. Now, for the sake of understanding this problem, I'm actually going to compute that. Okay, this is going to be 1.5 minus 2 all to the fourth power times the 3 divided by the 4 factorial. This comes out to 0.008 if you round it, okay? Here's what this is saying, you guys. If you guys had a graph and then you had the polynomial lookalike and you're saying that the error is at most 0.008, okay? So take a look. If I go back to f of 1.5 right here and I compute this, oh gosh, here we go. 1.5 minus 2. This is going to take me forever because I don't remember the value. To the third times the 8 divided by the 6. Okay. Plus, oh gosh, I would rather write this out. Hold on. Okay. Here we have negative 3 plus 5 times 1.5 minus 2. I should have brought my calculator with me. Plus 3 times 1.5 minus 2 squared divided by 2 minus 8 times 1.5 minus 2 quantity to the third power over no. There we go. Divided by 3 factorial. Okay, if you guys notice right there, it comes out to negative 4.958 if we were to round it. Okay? Please verify that with me too on your calculator, okay? This came out to negative 4.958. So check this out. That was our approximation right here. Our error tells us that we can only be off by 0.008. So what you guys do here is, now first off, finding the error is the same thing. Because that they're phrasing this question differently, we have to do a little bit more here, okay? So this has nothing to do with the Lagrange error bound. They're just asking us to explain why something can't happen. So there's a follow-up to it. What you do is, regardless if I take my negative 4.958 and if I add or even subtract the 0.008, I will not get negative 5. It's impossible. So even if I factored in my error, there's no way that that's going to add up or subtract out to negative 5. Okay? The big takeaway, you guys, just so that you're not clouded by this right here, the big picture is this. The next unused term. So it's going to be the maximum of your next derivative with your next degree with your next factorial. Okay? Let's do one more. Okay. Last one. Here we go. Okay, write the first degree Taylor polynomial for h about x equals 2. Okay, so h of 2 is going to go first. Then the first derivative, x minus 2 to the first over 1 factorial plus the second derivative, x minus 2. Now, you don't have to write this out, you guys. Actually, they just want the first degree, so I'm going to stop here. But I'm writing it out so that you guys can see where I'm getting my values, okay? All right, here we go. H of 2, according to that table, is 80. Okay? H prime of 2 is 128. All right? So we found the first degree Taylor polynomial. Okay, so now we have to use it to approximate 1.9. So all you do is you plug in 1.9. So that's just 80 plus 128 times 1.9 minus 2 equals equal. We're just going to leave it there. Okay, now I'm going to come back to that question later because I want to get to the error bound, okay? Here we go. Third degree Taylor polynomial for h. So it's going to be 80 plus 128x minus 2. The next one is going to be the second derivative. So 488 over 3, x minus 2 squared over 2 factorial, plus the third derivative at 2, which is 448 over 3, x minus 2 cubed over 3 factorial. So we went up to the third degree. We answered that first part of the question here. We want to use it to approximate h of 1.9. All you guys are doing, I'm not going to write it out, but you're just going to plug in 1.9 into each of these. All right? Okay. Use the Lagrange error bound. They were nice enough to tell us to use the Lagrange error bound. But if you noticed, this series does not alternate. So you know that you have to use the Lagrange error bound. So they were nice about it. To show that the third degree Taylor polynomial for h about x equals 2 approximates h of 1.9 with an error less than 3 times 10 to the negative fourth. Okay, in other words, the moment you guys hear the word error, we're doing this. Okay? Has to be less than. And this is where the magic happens, you guys. If it's the third degree that you approximated, the next one is going to be the unused one. So it's going to be the maximum of your fourth derivative. I should use h here. Okay? With the fourth degree with the fourth factorial. So here it's going to be the maximum of h fourth derivative of x minus 2 to the fourth power over the fourth factorial. We're going to evaluate this at 1.9. Okay. Now this is probably the trickiest part. How do you find the maximum of the fourth derivative when you're really close to 2? So let's take a look at our table. Our fourth derivative, when we're really close to 2, okay, what do you guys think it's going to be? Think about that. Press play whenever you're ready. Okay, when we're really close to 2, it's 584 over 9. Okay? So we have equals 584 over 9, 1.9 minus 2 to the fourth over 4 factorial. And because you know that this is right, you can be cool about it and just say that this is definitely less than 3 times 10 to the negative 4. Because that's what they're asking for. Right there. Okay? I'm actually going to squeeze in one more, you guys. I'm sorry. No, I'm not. Okay. We're going to jump to the last one. Hopefully we won't need too much. Let p sub 4 of x be the fourth degree Taylor polynomial for f. F is right here, you guys. Okay? So, I'm going to cheat a little bit, okay? So sine x squared is going to be Well, I know that sine is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and so on. So sine of x squared is going to be x squared minus x squared cubed over 3 factorial and so on. Cosine x is just going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. I think that's going to be enough. So f of x is this plus that. So if I take a look, it's going to be 1. Okay. Plus something x squared here. So if you take a look, there's a 1 and there's a minus 1 over 2 factorial. I'm just going to factor that out. Okay. And there's no other 4th degree except this one here. So I'm going to write x to the 4th over 4 factorial. The only confusing part is probably this. I want you guys to just think about it. If we were to smush these two together, you would put them all in order. But since we're only going up to the 4th degree, I know that these two terms right here are going to have to combine because they have the same degree. I just factored out the x squared, okay? So this right here is your 4th degree, all right? That's p sub 4 of x. Using this information from the graph that they give you up above, which represents the 5th derivative of f, show that whatever the heck that means is less than 1 over 3,000. Show that the actual minus the approximation gives you less than 1 over 3,000. That's code for error. All right? So, here we go. So our error, p sub 4 of x minus f of x will be less than or equal to. Okay, now if it's the 4th degree, the next unused term is going to be the 5th degree. That's going to be the maximum of our 5th derivative. Okay. To the 5th power over the 5th factorial. And we're going to evaluate this, kind of sneaky, at 1.4. All right. I'll try to squeeze it over here, but I don't know if I have enough room. So it's going to be the maximum 5th derivative. I'm going to leave some space for that. Times 1.4 to the 5th power over 5 factorial. Now right here, we need to figure out what the maximum is for our 5th derivative at 1.4. So take a look at this. Sorry, not at 1.4, at 1/4. Why am I writing 1.4? Why didn't you guys correct me? Just kidding. Okay, at 1/4. So 1/4, you guys, is right here. All right. What is the absolute maximum that the 5th derivative could be at 1/4? So if you notice, it hits the graph right here. But what's the most that it could be? You could easily say, because we don't know what that value is, you could easily say that that definitely cannot be more than 40. Because 40 is right here. And that is definitely under it. Okay? So that's the logic behind it. So we know that the maximum is going to be 40. All right? If you actually compute that, you'll find out that it's true, or you could be gangster about it and just say that it's 1 over 3,000. And then you're all done. Okay? Here's where I want to leave you guys. I don't expect you guys to be masters at this now. All right? But I do expect you guys to have an idea of where you need to go. We will get better and better at it as we practice more and more. All right? So in a nutshell, we use the Lagrange error bound when you don't have an alternating series. You always use the next available term, okay? Or sorry, the next unused term here. So here's what I mean to wrap this up. If you notice the series here, it starts off at a 0 degree, then a square, then an x to the fourth. Now, people would use x to the sixth for their next term. But remember, it's the next term, whether it's available or not, whether it's visible or not. So directly right after x to the fourth, we still use something to the fifth power, regardless of the pattern. Okay? Now, if this was an alternating series error bound, and you notice it goes by even degrees, then you would use x to the sixth. And that's where it gets tricky. All right? So just keep that in mind. And we'll practice as we go, but continue to ask a lot of questions because it's not so transparent at the very beginning. All right? Okay, I'm done talking.